Hi guys, my name is Ghani and we are Moose Mutant. My group members are Tasbiha, Murtaza, Rabia and Maheen. And our data structure is Fusion Tree. Fusion Tree is a sub-logarithmic data structure. It's an implementation of B tree with search time, log of n and linear space complexity. This is achieved using functions sketch and parallel comparison, which we'll explain ahead. The fast insertion, sorting and search of Fusion Tree makes it efficient to be used extensively in database systems. Our application is also a movie management and recommendation database system. Given are two references, which are published papers from the authors of Fusion Tree, Michael L. Friedman and Dan E. Villiard.
So I'll be talking about the challenges and the problem that we're trying to solve. So the major challenge that we're trying to address through Fusion Trees is to solve the problem of time complexity. Before we move ahead, it is important to know that Fusion Trees, they are a more optimized version of B tree, and as you can see in the table that's right in front of you, that algorithms like skip list, to some extent in the average case, these algorithms, they do provide the same complexity as the B tree, but in the worst case here, it is only the B tree that gives us the best complexity. And since Fusion Trees, they are a more optimized version of a B tree, they tend to be more time efficient, and Fusion Trees do that by several processes, and one of those processes is parallel comparisons, which Tasvia is going to talk about in the next slide.
So fusion trees are a lot like B trees in terms because one node can have multiple key values. That is very similar to B trees, and the same functions like split children and insertion and search are very much similar to B trees themselves. The only thing that is different between B trees and fusion trees is the parallel comparison and sketching technique. So parallel comparison is called upon every time some value is to be inserted into the tree. So for example, if one value is inserted in this node, then the tree will check whether that value is lesser than or greater than this node, or whether it should come in between any child node. This can be done by using linear iteration, but that will take a lot of time. That's complexity will be on. So to eliminate that, fusion tree makes use of the sketching function such that one value, the incoming value, can be compared to all of them simultaneously. And that sketching is a very similar method. It's a digital comparison that happens by converting all these key values into binary values.
The problems that we faced while implementing this project was that number one being that the fusion trees are integer based trees, and we have movie info in the form of a list based value, so inserting it in the fusion tree and performing functions on it was not possible. So what we did was insert the list and use the movie id as the value on which functions such as parallel comparison and sketching, etc., would be performed. The next problem that we faced was that with the sketch function, so the approximate sketch is used instead of the exact sketch because exact sketch cannot be computed in constant time. Perfect sketch requires the distinguishing bits to be compressed with a computation, which is an expensive operation. Approximate sketch doesn't try to compress the distinguishing bits together tightly. Rather, it adds a fixed pattern of zeros between every two distinguishing bits. This is done by multiplication with a predetermined constant. The result will be of order O of R4, where R is a count of distinguishing bits.
Conclusions that we have reached while working on this project are that when dealing with applications that make use of very large data sets and employ um, the search, insertion, deletion, updation mechanisms very often, it is very important to take into consideration the time complexity. As you can see on the graph to the right, here we're comparing log of n and n log of n complexities, and log of n complexity is near constant time for very large values of n, while n of log of n is more than linear time. So it is very important to take into consideration these complexities. And other than that, this is the end of our poster. We are near completion with our project. I would say we are 80 to 90% done. The only things that we have left are the integration of our updation and deletion into our GUI and code, and we might add some more time complexity analysis to our poster and make our GUI more user-friendly. Other than that, we're near completion and we should be done by this weekend. Thank you.